today. So this is like the beginning of some acknowledgments. This has been a really great project with a lot of partners. Certainly our MnDOT districts and the counties have done a tremendous amount of work with Geogrid and other geotextiles over the last couple of decades. So it's, all the huge amount of implementation already taken place. So this has been as far as research goes, one of the most fun projects I've ever been part of, because it's basically just doing the math to justify what the districts and the counties already pretty well understand. There's also been a lot of work by other states, DOTs, federal highways, and the contractors and equipment manufacturers have also done a lot of innovation in this area. In addition, this project, the current one I'm working on, is only the latest in a whole series of projects that universities and consulting engineers have helped us with. And finally, the U.S. Congress, I mentioned them because they've 2 years back passed Act 21, which is a required performance measure. A lot of the things that are related to the implementation of mechanistic empirical pavement design are performance-based things that haven't been implemented as readily or efficiently as they are being done now. So with that, I'll be going through this list of stuff. Just briefly, how we're using Geogrid in Minnesota, and then providing a framework for how we're connecting what's being built with our pavement design. So that's through mechanistic empirical pavement design, in-phase software here. Talk about how the construction testing provides us with the inputs that we need for pavement design. Get into, in order to understand how Geogrid works, we have to get the properties right, and moisture is critical in understanding how the aggregate bases behave. Talk about how we quantify the grid, and then wrap things up. So in Minnesota, you might notice that this is the Canadian border. One example of why Geogrid is important in the state of Minnesota up north, where a lot of these projects have been implemented. Some of the detours can be really extensive. So 72 is one trunk highway where we install a grid, and if you look at these potential detours, it's really important that we have options that don't require the entire roadway to be shut down. So here's when the grid was installed in 2011, this is the way it was able to be done. They were able to work on essentially half the road at a time, maintain traffic on one lane. So it's again provides an important benefit to the traveling public, not to have to completely disrupt their life during the summer. Jim sent me this photo out of the archives. It's similar here, I think, to the prior. It could be practically the same spot, but this was when the roads up north were built originally. Many of them were essentially sort of floated, not quite, but almost across these marshes. And so grid has been used more recently. And another reason to use this grid is that when you try to widen this stretch of road, the edges are going to tend to want to slide off. So the grid, from a strength standpoint, is holding that embankment together. So that was one of the reasons why grid was used initially. And what I've been involved with more recently is if you got the grid in there, what other benefits is it providing? How much is it really helping you with the long-term pavement performance? So in addition to this holding things together, there's other quantifiable benefits from the grid. As I mentioned, the counties up north in particular have been using grid for, again, a couple of decades, doing a lot of smart stuff with, again, trying to reinforce the local roads, and have provided a lot of experience to their network and ours. Another important thing to remember is that we maintain many thousands of miles of road. If you look at the map on the left, this is the current surface condition, the smoothness, and we look pretty good as far as the smoothness goes, but if you look at what's underneath, we've got a lot of roads that are going to have to be rebuilt over the next years. And so techniques like Geogrid and other things that strengthen the foundation are things that we're going to have to make better use of in the upcoming years. So I mentioned I need to talk about how mechanistic pavement design is part of this overall framework. It's how we're quantifying the materials with and without Geogrid. So there's both MnPave flexible and MnPave rigid. I'm going to be speaking completely today about the flexible mechanistic framework, and that's available. You can just Google MnPave if you want to try it out. You can download the software. It's available to anybody on Earth, essentially. And also what's important to note is that in Minnesota, then a couple of years back, we are exclusively now using mechanistic pavement design. So prior to that, it was essentially optional. You could use the empirical system we've been using for many decades, but for the last couple of years, it's only been mechanistic pavement design. So when you're using mechanistic pavement design, the inputs that you are required are more constrained, and that's what this project then is supporting, those new input parameters that are needed. This is just one of the input screens for MnPave. Basically, there's sort of three things that you got to provide: the climate, the traffic, and then the structure piece. So this is today I'm just going to be speaking about the structure again. How do we quantify the materials within mechanistic pavement design? And so if what are required are either laboratory tests or field tests. Somehow we've got to get at the mechanics, the physics of this problem and define the layers and the materials in those layers. So again, we've had this process. MnPave has been around as far as without the grid for, I guess the first time we went to training districts was in 2002. And so we've had most of the things I'll be speaking about today many of them have been there in bits and pieces, and then now more extensively since 2002. So I mentioned that the other part besides the framework of mechanistic pavement design, we can use the construction testing to provide these inputs. If we're going to, there's a couple options. You can either use the default properties in MnPave, which then have big safety factors. You can do laboratory tests, or you can use the field measurement. And MnPave has been calibrated and built on falling weight deflectometer testing, which is this trailer that we utilize around the state to go out and do in-place stiffness measurements with the falling weight deflectometer. So MnPave was initially built, and the way it's constructed is that it's calibrated to that field test. So not the laboratory testing, but to in-place field measurement. So the idea of transitioning then from the traditional type of construction testing, which supported the prior pavement design, that was based on density and kind of recipe specs. Now that we're into mechanistic design, we need to align our construction testing to that same framework as best we can. So that means that we're going to, rather than specifying a density of the material in the field, we're going to specify modulus and strength, and then link that to the design. I think it's important to note that this testing, this density testing, was, most of us know it, if you remember back to your soil mechanics classes, is attributed to Proctor. Talk about Proctor testing. And we're trying to sort of change to what seems to be a new thing. If you look back at the history, Proctor actually didn't use the type of density tests that we utilize today. He was building earthen embankments in California, and when he was compacting those materials with his team of inspectors, he was concerned about strength of these, again, earthen dam embankments, and the optimum moisture for compaction, and the need to avoid rutting during construction. So much like Same time that he was working on this, other people were starting to develop pavement design methodologies, and they also were focused on not the density, but the performance. So performance testing, and not about sort of the density of the particles, but about these performance-based tests. So again, Proctor himself didn't intend us to be out doing sand cone density tests. What he and his team were implementing was a performance-based test, and that was, as talked about here, the last bullet was a penetration test. So that's what Proctor was using in the 30s and 40s, not density testing. This is his penetrometer, and it's not too different from the dynamic cone penetrometer that we use here in Minnesota, which has been now implemented for about 20 years. So we're using the DCP, that's a performance-based test that feeds right into mechanistic design. That's good. We can use this along with Geogrid, so it all fits in the framework. We're also using the lightweight deflectometer. Some of the districts are using the LWD extensively. There's, again, national standards for this. This fits right into our mechanistic pavement design framework. And inside of MnPave, there are, just like the FWD, I mentioned the linkage between the FWD and mechanistic pavement design calibration. The LWD target values are estimated when you, for whatever properties you select, on whatever thickness of materials you select, the target values are estimated within MnPave. So the designer knows when they're designing the pavement what they should expect as far as the deflection measurement using the lightweight deflectometer during construction. And these are the different values that are shown here. These are based on the moisture content, the degree of saturation. So depending on the moisture condition in the field, you adjust these target values. If it's drier, you're going to have less deflection. If it's wetter, more deflection. So again, this all works with Geogrid, whether you got Geogrid or not. These target values would be adjusted based on the stiffness of those materials. Some of the benefits of these performance-based tests are that the inspectors that we are out there, these are easier to communicate with the contractor as opposed to the black box, or yellow box density test or sand cone, which are somewhat difficult to communicate whether this is good or bad. If the test passes, everything is good. If it doesn't pass, then people are complaining. But these, like a DCP, the cone goes in the ground, that's probably not very good. If the plate moves a lot, that's not good. Contractors understand this. Much easier to sort of get the whole construction team on board with getting a grade built that's adequate. The concept then of how we link up construction with pavement design is like this. You got your pavement design. I mentioned how that's kept and calibrated to FWD testing, how it predicts the lightweight deflectometer values. Then we've got the quality control being done by the contractor. Our inspector is doing the quality assurance testing, and then the pavement management going out and measuring the performance over many years. One interesting job that we built back in 2005 was the stretch of Front Highway 12, US 12 out by Wilmer. And when we were out there doing this intelligent compaction monitoring, we didn't see that. And when we looked at it, we noticed on the left over here, so on the west side, there were these stiffer material. Blue here is increased stiffness. And we were puzzled by this because you can see that the pattern is quite a bit different. We got a lot of sort of reds and yellows over here, and then right over here, there's a kind of a transition, and then it's these blues, which are a stiffer material. And so we asked the district about this. Again, we were out there when the grade that the trucks were hauling on the top of this aggregate base. It all looked about the same. But the district, oh yeah, no, that was a poor spot there. So we had to go in and write a special a change to the contract and out that there's textile, geotextile would go to the west here. And then when 15 years later, when we had some students over at the university that were interested in doing a capstone project, we got the pavement management data, worked with Shelley and Dave, and those students plotted up the pavement management data, and that's the red bars on top of the Intelligent Compaction data, which is the green on the bottom. So anyway, this is just an example of when you, during construction, if you map out the as-built layers, that then years later, you can compare that to the performance of the pavement. Similar to our implementation of pavement design, where we've got MnDOT policy that requires the use of mechanistic pavement design, we also have expectations for the implementation of Intelligent Compaction. This is working real well on the asphalt pavements. We're not building a lot of new grades, so we're kind of a little bit behind on implementation of IC on the grading work, but again, we have a system in place that would provide the same kind of as-built measurements, and then potential link that to pavement performance. So in summary, we've got these LWDs and DCPs that we've been using for many years. They're both used when we have grid and when we don't. We've got MnDOT policy in place that supports both the pavement design and the compaction monitoring, and there's an AASHTO draft specification that's available for this the full integration of the stiffness measurement with the with construction. So I mentioned how important it is to quantify moisture. Again, as we're going to get to grid here, the specifics of grid eventually, but before we can talk about grid, we have to get the moisture content, the moisture influences quantified within the pavement structure. As we all understand, moisture is sort of supercritical because it's wet either during construction or wet during when the road is in place, performance is affected, and so we need to somehow move from empirical knowledge to something that's math, math and physics. So again, MnROAD is a place where we're able to do a lot of this work, and so there's many case studies have been done. There are different types of projects. Some of the really important work was by Ruth Robertson when she was here, and then her thesis that she completed in about sort of 2008 kind of a time frame makes a lot of important lessons, or lists these lessons learned, which I'll just mention here briefly. So, for instance, we understand that the modulus, the stiffness of the material, and the strength are greatly affected by moisture. And the way that that's quantified is there's actually little bridges of water between the particles, and those little bridges of water create a kind of a tensile stress, a connection that's like a little elastic rubber band, or however you want to think of it. And that depends on, as is mentioned here, the quantity, so the gradation, the shape of the particles, the porosity, and actually how much water is there. And here's a figure that tries to display that, where you can see that the sand grains are those particles. You've got air voids, and then the water between the sand grains, or whatever particles between the air bit and the smaller particles, you've got these water or moisture bridges. And this is the same sort of physics, trees, for instance, or plants. Trees, there's no pump in there, there's no heart. The way that the water gets up into the tree is the vessels, or that length of the groundwater to the tree canopy. So you've got real thin, like a straw, except smaller, so that the water tension, capillary action, you maybe heard capillary action, it draws water up tens or hundreds of feet into trees. So this same force, the same pulling action, is what's happening within soil. so this provides an additional stiffness that was considered in mechanistic pavement design. So back in, again, when this was first laid out in 2000 time frame, we had these seasonal factors, which are still in there. This is still what's in place. And for every material, we have a set of seasonal factors. So and this relates to the seasons of the year, of course, but as we have these 5 seasons for those years there. But that comes from, those are really moisture influences. So there's the winter is froze, but the other times of the year, the moisture is what's changing. And so these seasonal factors that are currently inside of MnPave are based on moisture content. And they were empirically derived at that time, and now we're, with this modeling I'm describing today, the potential is that they would be somewhat modified based on the new work. But anyway, inside of MnPave right now, this is the unsaturated soil mechanics framework that again was put in there 10 years, dozen years ago. So it's essentially the foundation has been laid for within MnPave to link together this mechanics piece. So you can't get into all the sort of details today, but the bottom line is that, again, the sort of foundation's been laid between linking up moisture content measurement in the field, something we would do today, or we have been doing, measure moisture content, and then turn that into a suction. Again, this ability of the materials to be pulled together, those quantification of the pulling action between the particles. That's all that stuff has been started. So when you look at these factors, these moisture factors within MnPave, I want to just point out a couple of slides up on this page, but I'll just real briefly. Again, the seasons are over here on the left. So in early spring, if you think about how that moisture content relates to optimum moisture, we're at about 95% plus minus of what we might think of as an optimum moisture content, standard sort of Proctor measurement. Late spring might be sort of 85, fall 70, and in summer about 65% of optimum moisture. Again, relating the mechanics that's in there, if you turn those moisture measurements into the suctions, these are sort of suctions, and then the modeling that's been taking place for the last couple of years here creates an estimate of this gain factor. So, for instance, the difference if at early spring the aggregate base, the moisture factor is a 1, if that's our standard, then as you move to summer, you're going to have a gain factor, an increase in stiffness by 2.3, 230%, or a factor of 2.3. So the difference between the spring condition and what you're going to have in the summer, that aggregate base is going to be roughly a little more than twice as strong. That's what this gain factor is. So again, I mentioned that historically we built in these seasonal factors in MnPave, a dozen, 15 years ago, and they're showing here the existing aggregate base. Those factors are 3, 6, 8.84, and 102. What's being done now with this numerical modeling, these are the factors in red that are currently coming out of numerical modeling, which is really similar based on how we did it 15 years ago. It's interesting that the mechanics are supporting. They are the empirical measurements that were done 15 years ago. This is very encouraging. So finally, we're going to get to how do we quantify this grid. So again, we have the mechanistic framework, we've got the construction testing, we've got the moisture sort of figured out. Now we add grid to this system. How do we do that? So as a reminder, here's what we're actually building in the field. This is the good work being done by Jim and the district staff. They've got this down between them and the contractors. They've really got a neat system here. And again, that allows them to build half the road at a time, moving the material across the grade, laying down the grid, compacting the material back, and again, all this time maintaining traffic on this operation. What's being, one example of what's been built is this configuration where we've got that reclaim material, about a 9-inch lift of that reclaim material, and then we're putting the grid sort of midway up in that section. So it depends, again, this is the example I've been focusing on is looking at sort of 9 inches of reclaim material and then the grid at mid depth within that section. And so when the district was building these things, they left some amount of control sections, or tried to, so that you'd have a comparison between the influence of the grid and with and without. So you'd have a section that was pretty close to the same with and without grid. That was the idea. Unfortunately, when you actually do this, you're not going to get identical sections. You're always moving down the grade. The soil's always changing a little bit, and maybe not just a little bit. And so when we try to go out and measure this in the field, it's been difficult to show the clear benefit of grid very precisely. What has been done and what we've hired Tech to do some FWD testing. We've also used our own FWDs on these roads, and we've gone out there and again taken measurements in locations where we know there's grid and where there isn't grid, and then we compare the two things. What came out of that was very overall very positive. You see that if you look at the grid reinforced pavements on the right side of this graph, you see that the geogrid generally is showing an increased granular equivalency. Now this GE is the old pavement design system, so this doesn't really help us a lot with anything that's going to be plugged into MnDOT. But it demonstrates that for the grid is providing some kind of benefit. And from this, it would look like, if you look at the averages here, the average the control no grid sections maybe have a sort of an average of say 33, and the grid reinforced sections might be at a 37. So it's sort of 4 or 5 inches of increased structure. And what the local research board has implemented is it 2 inches or 3 for 2 inches? 2 inches for grid. So when the locals use grid, state aid gives them a credit of 2 inches for the installation of grid. However, for again that works on in the old pavement design system. It doesn't work for MnDOT Mechanistic pavement design, and MnDOT never allows this compensation on the trunk highway system. And so that's why I was asked to work on this, because can't we somehow quantitatively show that this grid has a positive impact? And so we moved on from the visual data to the measured FWD analysis, and now we're back to MnDOT again. So we've got to somehow work quantify this effectiveness grid into MnDOT. There's all we've got to work with here are the stiffness of these different layers. So we've got a stiffness now. Based on the FWD testing, the LWD testing, we've quantified the grid. We've got the effect of moisture. Now we've got to add the grid to this system. So it's possible you could look at laboratory testing. You could create some kind of a sample, no grid, run the modulus testing that we've done. But as I mentioned, we don't use this testing. We've spent a couple of decades, at least a decade, doing resilient modulus testing, and essentially we don't have a database that's sufficient to quantify Minnesota aggregates, Minnesota soils using lab data. We've calibrated our system to field work with an FWD. So this, even though other states are kind of pursuing this angle, we're not using laboratory tests. And you can imagine, as I sent this piece of grid around the room here, it'd be difficult to get any kind of a reasonable, accurate test if you put a piece of grid inside of that. This sample here is like a concrete cylinder, essentially, inside, 6-inch diameter, 1 foot high. So if you put grid in there, I don't know what kind of measurement you get as far as an estimate of strength. So again, back to the field. Dave White's company. We know Dave from his work, prior experience at Iowa State. Now he's on his own with a few of these rigs and staff that are running around the country quantifying the in-place stiffness of materials. This automated plane load test essentially can simulate the resilient modulus test that's done in the lab. So this fits right in with what we're trying to do here, because again, we've got a field calibrated mechanistic empirical system. We use resilient modulus, so which is really this repeated load. It's not the FWD per se. The FWD is a single drop. This is a repeated load test. So this fits, even more closely with the how mechanistic pavement design is sort of the repeated loading of trucks fits into the design. So then we took this numerical modeling. How much time? Can't see it. Yeah? Okay. Pretty good shape. I'll try to get this wrapped up so we can ask a couple of questions. So again, back to numerical modeling. So since we've got this computer code work that I tasked to work on for us that helped us with the simulation of moisture content, we can add grid to this system. So we've got a box that's this cube that's essentially 1 foot on the side, and then can model the depth, the layer thickness. And so now we can install this grid, and we can get the proportions right. So we've got the scale effects seem reasonable here. And when we looked at this, if you got that much grid, you've got a pretty representative system. If you shrink that box down too much, so you only got a couple of grid, square grids within the box, you don't get a fair test. But if you got this much grid, then you start to replicate what you measure in the field. So the scale is big enough, and you're able to run these models in a time frame that's sort of reasonable. So what's been happening over the last couple of years and with this project is we've looked at these parameters, the area gradation. So we're using essentially class 5Q, coarser gradations. We're looking at the effective friction between the particles. So even though you see spheres, little balls, the way we model the interaction, the roughness of the particles is through the particle friction. So that can be increased so that essentially you end up with what would be angular behavior of the particles. The stress, that's how tightly it's held together. The loading from the vehicles, the trucks, and then how tightly it's confined is this confining stress. The moisture content, which I talked about earlier, is in the form of this tensile stress, and then where the grid is inside that layer. So this, you zoom in here a little bit. The grid then, this is with, well, the upper left corner is the class 5Q gradation, again spheres, but the roughness of the particles is increased to simulate angular material. And then the grid, if you essentially erase the particles, you can then see the grid, see the information of the grid. And one thing that, how does this, as part of an explanation of how does this grid actually work, what goes on, is that the red here, again, this is, the balls have just been made clear. And so the grid, the red is in tension, and the black ribs are being compressed a little bit based on how the rock is impacting that grid. So the idea, or what's happening here, is that the grid is acting like the steel under in a beam or in the roof here. Is that the grid is being put in tension, and so it's confining the gravel around that grid. So this is the mechanics that other people have demonstrated in other ways, but that's what's sort of happening inside this model. So then if we build models inside the computer with and without grid, we get this type of data. So this is on the vertical axis is the stress, and the horizontal axis is the strain. This is the resilient modulus kind of a test. You've attended some of these things in the past when Dye has explained resilient modulus testing or others. This is the type of test that we do either in the lab or in the field with the FWD. We have a resilient modulus. The slope of the line is the modulus. So this, if you look at that red line, this is without the grid, no grid. Here's with the grid. So again, we're doing this cyclic resilient modulus testing, and we see a benefit due to this grid. This is the change in stiffness with and without the grid. If you compare those two things, that's what we're proposing to, and we are beginning to implement inside of MnPave, is the difference, this grid factor is the difference of the aggregate base without grid, because we've got all these, that's what MnPave is currently functioning on. We have a resilient modulus for every material that we're currently using to build roads, and if we add grid to one of these layers, we would expect these gain factors to be relevant. So how does this, we're on about the last slide here, how does it all come to anything? Okay. So for instance, on this chart, we've got on the vertical axis is the fatigue and rutting damage inside of MnPave. So right now, when you do a pavement design, you get a value. You have to design a pavement that the fatigue and rutting are less than 20-year design life, but that equates to a damage of 1. So if you look at the vertical axis here, on the gold line is the fatigue and the red line is rutting. So and on the left side is the gain factor. So if you had no grid, you'd have a gain factor of 1, right? No grid, 1. It's the multiplier. So what at the beginning, when you don't have any grid in your system, this pavement is not going to make 20 years because there's more damage. Damage is more than 1. It's going to fail before 20 years. So what kind of grid factor do you need to get this pavement to last for 20 years? So as you move to the right across this, you can see that the fatigue is not impacted. We don't need much to help us with fatigue. And again, that sort of makes sense. The fatigue is in the asphalt. That's not going to be benefit. They're going to benefit from the grid very much. But the grid is helping with rutting. So as you move across here, you're going to need a grid factor of somewhere between 2 and 2.3 to have this pavement make it to 20 years. And if you remember from the prior slide, these grid factors are coming out, based on this huge parametric study, anywhere between like sort of 1.5 and 2.5. So again, depending on the structure, the grid factors change. But the bottom line for today is that grid has a quantifiable benefit, and it's just as the districts are showing up, is that they know empirically, they know by observation that the pavements are lasting longer when they have grid, and this demonstrates quantitatively using our current mechanistic pavement design system that this is sort of why that can be understood. So the bottom line is, as far as conclusions, we got the construction testing, LWEs and DCVs we've been using for 20 years. We've got moisture quantified. Now we've got an explanation of why this grid works, and we're just again pressing forward here with implementation so that the districts and our other local partners can continue to use this grid and also justify it quantitatively as far as in their plans and design. So with that, going back to my moon story that Bernard mentioned at the beginning, and take a couple of questions. If,
you guys thought it was a joke, it was true.
Yeah. All right.
Any questions for John? Any questions from those who are participating online? Okay, Jim, I'm going to put you on the spot. Jim Bittman? Jim, my friend, are you there? Jim?
I can put Jim to sleep, so let's do that.
Oh, Jim had another class that went on the same time.
Okay, all right. Any questions from here? Okay, here's the mic.
I have a question.
Yep, go ahead.
Go ahead.
You guys were just looking at Geogrid. Has your work extended to, geotextile fabrics at all? And do you have any kind of a cost comparison for using a grid versus other alternatives, like maybe a thicker aggregate base or something like that?
So this project is specific to grid, and so we're not doing anything with, as far as this particular project with textiles. But there's other states, other work. If you want to I can provide a couple references for people that want to get connected to other work. There's just recently going to be a report published within a month or two, that national report being completed by one of the universities of Texas that includes textiles. So that's something that is going to be hopefully very useful to many people. It will include both grid and textiles, and it's got a national panel behind it. So that'll be good.
John.
Yep.
Great presentation. My question is, it may not be directly related to in soil, but there were studies applying geotextiles or any kind of textiles in asphalt pavement, and to prevent the reflective cracking. And it turned out to be there had issues with the compacting around those geogrid areas, and as a result, it kind of causes a debonding in those areas where they install the geogrid as you know, it's critical to it's important to have a proper bonding between layers in asphalt pavement. So what's your thought on installing geogrid on soils in terms of bonding on those areas?
Well, so this particular project and the modeling that's been done with this, it has been, we're clamping, the grid is within the aggregate base. So you got rock, gravel on both sides of the grid. So you got optimal interaction between the grid. And this has been demonstrated by other people, both in the laboratory and then with other types of modeling, that you need to have this interlock with the grid. So, and you know, there's if you have a typical way to install this grid is between the granular layer or the soil and the aggregate base. So you put it, you sandwich it, you put after you built it, then you put it there. Okay, well that's, you know, there's a benefit that's been measured, but I haven't included that type of modeling here. And you can, sorry, excuse me. You can imagine it's maybe not be as good. You know, you've only got the interlock, the really good interlock on one side of this system, and it's probably not going to be quite as good. You're going to get some benefit, but not as much. So I don't know if that maybe sort of true.
Thank you.
Yeah.
Just one thing, John, very quickly. There is an aspect of this study you are doing right now that's looking at the third dimension. Could you just shed, for some seconds, shed some light on that aspect?
So we're continuing this. So we're grateful for the cooperation of essentially MnDOT at the beginning, because they shared with us, they gave us all the work that was done for one kind of grid. But now the second part of this is so all this initial work was done with essentially one style of grid. Now what's being done right now is that we're modifying this code so we can build any kind of geometry. It doesn't have to be square, it can be triangular, and all the rib thicknesses can be changed, the properties of the plastic can be changed, so we'll be able to create a performance spec that's independent of any proprietary data, essentially.
John, along those lines, John, you know, there's a wide variety in the properties of all the geogrids that are out there. Is there anything we should be specifically looking for if we're going to incorporate it into pavement right now in terms of properties?
So again, as I mentioned, anyway, right now in Minnesota, the leaders, you know, people who actually built these roads are up north. So Jim Bittman has a spec that supports the type of grid that's being used here. So it doesn't say use tensar, but it says that somehow it's appropriate to get the material that we need, because we can't, you know, it has to be a grid, it can't be a textile, and it's got to be a grid that has certain stiffness properties. Obviously, in this model, it's very precise. It's mechanics, and it's certain modulus of the plastic, it's certain dimensions of the grid, and so that and that again was all
But the one picture that you had up there, where you had the balls were shown in clear, and you just showed the grid in either tensile or compression, it looked like the majority, right there, you just passed, there you go. You know, you look at that, if the only thing you're worried about is a tensile force in those particular connecting pieces, you know, the stiffness that tensile has is kind of immaterial, isn't it? I mean, any grid that's got an aperture opening that's large enough to catch the angularity of the rock and provide that tensile strength between the nodes should suffice. So even some of the alternatives besides tensile should work in this picture here. Is that correct?
And that's why, again, we're grateful to tensile to give us all their internal R&D stuff. But the fact that what makes it non-proprietary or whatever is that they lost their patent. That's one of the reasons and so anybody can build this grid now. They can build this geometry. They can use plastic. And so we're going to have a performance spec that says, just here's the geometry. It's got the squares have got to be this big, or in some range. The ribs have got to be so big. It's got to be this kind of plastic. But it doesn't have to. We don't have to, because many manufacturers that you just said can build this stuff now. But there's different ways, whether it's this rigid grid or whether it's made out of something that the way it's manufactured could be less rigid. So we're going to need to specify the rigidity of this grid. Again, it's not going to say tensile, but there are tests that are available that define the rigidity of this grid.
Right, but according to this picture here, it doesn't look like the rigidity is the important factor. It looks like the tensile strength of the material itself is the important factor, not the rigidity.
Well, I guess they're both related, but it's also the geometry of the ribs relates to both these things, right? The diameter of the cross section of the individual ribs, just like the cross section of a steel reinforcing bar or whatever, is important. So that's what we're going to have to define. And then right now, I say, like on the ground, to get a grid that will work as expected, it's people like Jim Bittman who have got a spec that seems to get what they want. I don't know the details of how they get this done, but the fact of the matter is they seem to get it done. So,
okay.
So maybe I'll talk later offline.
We can, for more details about that, I'm sure John can exchange emails with you or talk with you, and the person who called online, so you need to identify yourself.
Steve, they have people.
Oh, Steve. Oh, okay. Steve, we'll get in touch with you.
This is Bruce Tanklet. I was just going to add something to the stiffness question. I think a lot of the benefit comes from not just avoiding the grid breaking, but also restricting movement. So that's where the thing that comes in.
That's great. It is, yes. Yes.
All right. Any more questions?
Oh, Bruce touched on it.
Oh,
I was just going to say that if the strain characteristics of those, the grid, the properties of the material are, if it's too soft, it strains too much, you're not going to set up enough restriction of movement to provide the confinement that you need. So
that's the modulus
is important.
Yeah, so the modulus of the plastic. So that there's a Young's modulus for the plastic in this model, and that is defined. Essentially that's part of the current ASTM spec.
Did you run any sensitivity?
No, not yet, because then we'll get into that more for this next phase of this, when we're actually able to change the geometry of the properties of the grid. We'll get into that more. But there's only so many kinds of plastic, so we don't have to worry about that too much.
Just one more question. Feel free to stop John Siekmeier, Blake Nelson, Amanda Singh, Jim Bittman, anything that has to do with Geogrid. Any more questions?
Thanks a lot for your...
All right, thank you. A round of applause for John Siekmeier.
for the people that are online or on the phone, just wanted to tell you that the Pavement Conference is coming. I know a lot of you that are online are probably already on your way, but tell other people. Tell as many people as you can. We need as many people at the Pavement Conference in May as possible. I need to get it for a second. Let's see. The registration form is live and the agenda is live. Let me see if I can find that for a second. Pavement Conference. There's the agenda. We've got both days all mapped out. We're deciding on the case studies as we speak, and the registration form is live. Yes, it is. So thank you very much. Thanks for connecting to us online.
Good.